All right, so they're going to ask you, or they're going to present, and tonight's homework, they're going to give you that P of 1. They're going to tell you what one to use. So if I'm able to show this is true, okay, that's the idea. If P of C equals 0, then X minus C is a factor. Does that make sense? That's one of these statements that we've had previously. If P of C is equal to 0, so you evaluate at some X value C, and if it gives you 0 back, that means the Y value is 0. So that means the X that you chose that was the C value is paired with the Y value of 0. Graphically, that's an X-intercept. And algebraically, that's a factor then of your polynomial. So the way we want to do this, you can do this. You can go P of 1 equals 1 cubed minus 7 times 1 plus 6. And that will give you P of 1 is equal to 0. You have shown what they asked. Does that make sense? But that's all you've done. Okay? We've shown that P of 1 is 0. That allows us then to make the argument. We can go a little bit further. We say X minus 1 then is a factor of P of X. So P of X will now look like this, where this is some X squared, that's something to the first, and then that's some constant. So it gives me the ability to take P of X, which is a cubic, and factor it down to now X minus 1, which is a linear factor, times this second set of parentheses, which would be a quadratic factor. Now what stinks, doing it this way, doing that substitution route, is I don't know what that quadratic factor is. I would have to go through synthetic division now, long division now, to find out what that quotient is. Does that make sense? I don't want to do that. Okay, I want to, especially since I have other tools, I want to try something else that is much more efficient. So we're going to do, instead of showing that this was true through substitution and evaluating, we're going to show this is true through the use of what we call the remainder theorem. Okay? I'm going to put the 0 there, okay, my C value, and then I'm going to put my coefficients for my polynomial P of X out here. Make sure you put a placeholder there for the X squared term. And now we're going to do synthetic division. So I bring my 1 down, multiply by what's in the box, put that product right there, add straight down, multiply by what's in the box, put that product right there, add straight down, multiply by what's in the box, put that product right there, add straight down. When I add straight down, what do I get here? 0. So that confirms what they were asking. Okay? That's using the remainder theorem that said if your remainder is 0, then P of the C that you use, so P of the 1 here, is 0. Okay? Now, why do I like that? Why should we like that better? Well, if this is a 0, then working a little bit backwards, X minus 1 must have been a factor. Does that make sense? So X minus 1, so when I rewrite P of X minus 1 is my factor. Okay? Now, previously up here, we didn't know what should be right there. We didn't know what the quotient ended up being of P of X when I divided by X minus 1. But now, with the synthetic division, if this was X cubed, what is this? X squared. Now, remember, that's your quotient, right? Now you know that this is X squared plus X minus 6. Okay? When you do synthetic division and you get a remainder of 0, that row of division ends up being your quotient when you divide by that linear factor. So, just some terminology here that I think is important for us to understand. That is a linear factor. meaning that the exponent is 1, right? Okay, so what is this one called? The exponent is 2. Quadratic factor. Okay, now, we haven't formally said this yet, but every single polynomial you come across through the use of the factor theorem, the remainder theorem, and the fundamental theorem of algebra, every single polynomial you come across can be factored down to a product of linear factors. Okay? Much like any number you come across, give me a number.
7.
Give me a so 7 is kind of easy because 7 is equal to 1 times 7. Okay? So you can break it down to a product of prime numbers, right? 5 is another one that's kind of easy, 1 times 5.
59.
Okay, so we get, does that break down to 3 times 23?
Yeah.
That make sense? Okay, breaks down to a product of prime numbers. Okay, give me another number. Give me a more composite number.
720.
Okay, so 720. Okay, that breaks down to, so it goes to 72 times 100, right? Okay, so, sorry. Yep, 72 times 10. 72 times 10. So 72 is what? 36 times 2. 2 times 5 is 10. So 36 goes to what? 9 times 4. So that's 3 times 3 times 2 times 2. Okay, so that's 36, right? And then I still have those. So times 2 times 2 times 5. That's the prime factorization of 720, right? Okay? So every number you come across, you can factor down to a product of prime numbers, right? Polynomial-wise, every polynomial we come across can be factored down to a product of linear factors, much like real numbers are able to be written as a product of prime factors. Does that make sense? Okay. So we should be able to continue factoring this thing because that's quadratic. That's not linear yet. Okay. So I'm going to rewrite my linear factor of x minus 1 here. But when I look at x squared plus x minus 6, can you rewrite that as x minus 2 times x plus 3? And now each one of these things is a linear factor. If you were to FOIL that all out, okay, you will get back up to x cubed minus 7x plus 6. Okay? Why would I want to do it this way, though? What does that benefit me in regards to graphing? What does that tell me? It tells me my zeros. Okay? So I'm going to graph this thing. We know a lot. We know that if we could do this from the original P of x that they gave us. All right, hold on a second.
Did you ever fix that malware?
I think so, but this thing doesn't want to ever cooperate. Like for some reason, inside OneNote, after using the drawing pens for 10 minutes, they don't let you like click and select them anymore. All right, so the idea here is whether I look at the original P of x or I just multiply these terms together, my constant ends up being 6. Okay? It's that right there, right? Isn't that my y-intercept? So in graphing this, I know my y-intercept is at a height of 6. I know here, x minus 1, x minus 2, that's giving me 2 zeros there. And x plus 3 gives me a 0 over there. X times x times x is x cubed. So I know my end behavior should be like that. Does that kind of make sense to everybody? So you see how we're filling in some information that's very useful? I know it's a cubic, so if this is my n value, n minus 1 equals 2, right? So I should have 2 turning points. Okay, 2 maximums or minimums. Now, I don't necessarily know where those are. Okay. All of these had multiplicities of 1, so when I go through these, it's going to be kind of a straight shot through, right? Does that make sense? Okay. Now, I don't know, I'm going to guess here, but I don't know for certain whether moving from this left-hand side, that whether I reach a maximum here before I start falling back through my y-intercept, or if I meet that y-intercept and then fall through. Does that make sense? I'm going to argue, I would think it's most likely this here, that I'm going to hit that y-intercept on the way down. Okay? I know close to the 0 my behavior, so that's why I made it solid. But now, between that x-intercept and that x-intercept, I'm not certain how low I'm going to go. Just make it dotted. And then here, I know that my end behavior should match up to that. Gives me a pretty good sketch of what my graph should be, right? Okay. Does it? Now, I didn't use the turning points to graph, but knowledge about my x-intercepts, knowledge about my y-intercept, knowledge about my end behavior, does my turning points kind of allow me to check to see whether I think I've done things correctly? Yeah. Should have 2 turning points, and that's exactly what I have here. So I feel like I'm comfortable with what's going on. Okay? And that's really what this chapter is about, guys. So far, just collecting information, collecting facts that we know about all polynomials so that we can kind of take all that information and put it together inside one graph. Okay? And all that information should kind of confirm and validate the next piece of information. Is that something we can do?
Yes, sir.
Okay. Let's go. If they ask me here to show that 1 gave a remainder of 0, right? Could they have tried a 2 instead? Once I know that x minus 2 was a factor, you know that 2 would have produced a remainder of 0. So let's just try that real quick. If we start off with 1x cubed minus 7x plus 6. So there's my p of x. So x cubed minus 7x plus 6. That's your original p of x. They said first find p of 1 to be 0. Well, once we did that, we were able to factor. We found 2 was also a 0. So if I put 2 there, let's see if that makes sense. If I bring this 1 down, multiply, replace, add straight down, multiply, replace, 4, gives me negative 3, multiply, okay. So now here's the thing. So does that look different? This is going to be x minus 2, x squared plus 2x minus 3 equals 0. What's that factor to? X plus 3, x minus 1, right? Is that the same? Is that the same factorization that we had right here in red? I have an x minus 1, x minus 1. We have an x minus 2, there's the x minus 2, and x plus 3, there's an x plus 3, right? Okay. Now I'll show you one more thing. We now know that p of 3 was also, or p of negative 3, p of negative 3, come on, ended up being 0. So here's my question. If I have 1, 0, negative 7, 6, if we tried that one, okay, bring my 1 down, multiply, bring it down, multiply, negative 6, multiply, gives me a 0, right? That right there tells me x minus 1 is a factor. Now, I'm not going to start, I'm going to just basically start over with my synthetic division right here at this line here. I'm going to put a 2 right there. Bring my 1 down, multiply, gives me 2. Add down, multiply, gives me 6. So give me another 0 right there. Okay. So what's that tell me? It tells me x minus 2 was a factor. Now think about what we started with. This was x cubed, right? What would this line right here, what would that?
X squared.
X squared. And I divided an x squared line by a linear term. So what's this one going to be then? X. Well, when that's to the first power, isn't x plus 3 what that's saying right there? This was saying x minus 2, and this was saying x minus 1. There's your p of x that way. Okay? So you can continue, and this is what we're going to do here in the next day and a half, 2 days, 3 days, is we're going to do a lot of synthetic division like that, and it's going to maybe be, 3, 4, 5 consecutive zeros that we're checking to see if they are indeed factors. And the hope is that we can continue to go through and say, oh, I got one, that worked. Okay, keep going. This is another one, it worked. So these are factors, and eventually get it down to either a linear factor or a quadratic factor, and then move on accordingly to completely factor this thing. Okay, so let's do one more here. Let's go. So some of your questions are going to say something like this. Let p of x equal x cubed minus 4x squared minus 7x plus 10. And we'll say determine if x minus 5 is a factor of p of x. Go ahead. Yes?
You see how they said determine if x, like how they're trying to give us a hint or whatever?
Yes.
Is that ever going to be wrong?
Yeah, it could.
What would we do then?
So you would just say, so they might, like on WebAssign, if they were asked this question, it's probably going to say, they'll probably have a bubble that says, yes, it's a factor, and then they'll ask you to type in, like, what was the leftover information. And then they might have a bubble that says, no, it wasn't, and they might have, like, reasons of why or something like that. Does that make sense? So they'll be able to tell you. And the reason, if it's not a factor, the way you determine that is you look at your remainder, and your remainder is non-zero, then it's not a factor. Okay? If your remainder is 0, then it is a factor. Good question. On a test or a quiz, if I were to ask that, I would want a response. I don't want you to just say no or yes, okay? Because that just tells me 50-50, you didn't really know. I want yes, it's a factor because the remainder theorem says if my remainder is 0, then C is a factor. Or I would say no, because the remainder theorem says if C is a factor, then the remainder should be 0. Or if C is a 0, then x minus C is a factor, and then P of C should equal 0. In this case, P of C does not equal 0. Does that make sense?
Okay.
So my remainder is not 0, so I don't have a factor of 0. You're going to find out, and I don't know if I've said this before, you're going to find out you're going to get college professors, whether it be in science class, math class, whatever. Some are going to be like, I just want answers. Some are going to be, I want answers, but I don't really care about what the answer is. I want to know why you know that to be the answer. I want your explanation. I want your logic of why you're coming to that conclusion. Okay. So I want you to kind of build that skill. Here we go. If they say x minus 5 is a factor, there's other ways that they might present this. So they might say 5, determine if 5 is a 0. They might say root, okay, or they may even say at times x-intercepts, okay. So there's different ways they can phrase this, but it really means to us the same exact information. It's trying to lay out the same process for us. So we're going to try to divide this thing. Remember, if x minus 5 is the factor, and x minus 5 equals 0, the answer to that equation is what you put in this box. Okay? So make sense, everybody? So if they would have given you just 5 as a 0, 5 goes directly in the box. Okay? If it's to give you a factor, then you got to solve that and put that in the box. So now I put my coefficients, 1, -4, -7, 10, and now work our way down. So the algorithm says bring that 1 down. Is everybody okay with that process? Now, all the examples we're doing here, guys, it's really nice, easy multiplication. I'm not saying that's always going to be the case. There might be fractions that, in certain cases. Might be large numbers, very small numbers, whatever. But that the process is the same regardless of whether they be integers or fractions. So, does that mean that x minus 5 is a factor? When I get that right there, is x minus 5 a factor? So x minus 5 is a factor because the remainder theorem says it is when you get a 0 as a remainder. Okay. If that would have been like a 10 that I got back, that would tell me it's not a factor, right? That's kind of the question and discussion Blaze and I were having there for a moment. So x minus 5 is a factor. Doesn't that mean that this here is also a factor? Okay, so p of x can be rewritten as x minus 5 now times x squared plus x minus 2, linear factor, quadratic factor. Can I factor that quadratic factor further? Yeah. Factor that quadratic, it goes to x plus 2x minus 1, right? Now just thinking about your graph real quick. It's cubic. In behavior is that and that. Your y-intercept is 10. You now have a x-intercept of 5, an x-intercept of 1, and an x-intercept of -2. So maybe your graph looks something like that. But it allows us to quickly get that without having to rely on our technology. Okay. I think it would be interesting. So we use, GeoGebra, we use Desmos, we use UTI 83s, 84s, and I don't know if this would be the case, but I think it'd be interesting to be able to get into the programming of those and to actually read the coding that allows us to type something in and it spits back the graph instantaneously. Because my argument would be that they're probably not doing the process of choosing x values, evaluating into that function, getting a y value back, collecting all those, and then plotting those, and then connecting the curve. My thought is that they're probably using a combination of this to find the zeros. So in the back route, when I type in the input for user, it's going to take that information, it's going to run it through and do this stuff to it, find the zeros. It's going to find the y-intercept, okay, by picking that stuff off. And then it's probably going to then attach to it a little bit of calculus to find maximum minimums. And it's going to plot those key points and then draw the curve through those key points. Okay, so this is, even though in the end result, guys, and we'll get towards the end of this course, we're going to rely on our calculator to do a lot of this. But I think it's important to understand how that calculator is working. The next thing I think is important, let's talk about this. Let's say that I have a cubic. And I don't have a specific example of this right now, but we can talk about this concept. Let's say I have P of x is like AX, or A times X, cubed plus BX squared plus CX plus D, something like that. And I start factoring this thing, and it factors down to like x minus some constant, let's just say f. And now I've got this, I don't want to use the same A, B's, and C's. So let's just say like g x squared plus hx plus j. So factors down something like that. But let's say that this thing here is non-factorable using our product sum technique. It's non-factorable by using our AC method. What should I turn to if that quadratic is non-factorable through those?
PQs.
Not P's and Q's, not yet. You could, but not yet. And I would argue that whenever you have a quadratic, never use P over Q, because it's going to be too time consuming. You got better tools. It's like using an abacus when I could be using a calculator. It doesn't make sense. Okay.
I don't know what.
You know what an abacus is?
Is that the circle thing that we use in
Yes.
school?
Yes.
Negative B over 2A.
No.
I don't even know what PQ is. We talked about that yesterday.
Quadratic. If I want to factor something, I always my safety net is always a quadratic formula, right? Okay. Now here's the thing: the quadratic formula sometimes gives you back one solution, and that's when basically your discriminant becomes 0. Okay. And for us here, that would mean that we have a double root. Okay. Sometimes it gives back 2 real solutions. Okay. And that would be nice because that would tell me that I do have 3 x-intercepts. But doesn't the quadratic formula sometimes give me back something like that? With negative numbers underneath the radical? Okay. If that would ever happen, because it will, okay, we might end up with something like maybe like x minus 3. Let's go like x plus 2i, x minus 2i, something like that. Okay. Do you know how to graph 2i and negative 2i?
Nope.
No, you don't. Okay.
Do you?
Yeah. Okay, so right there's 3, right? Okay. In behavior is that. That's the only, so this is the real axis, right?
Yeah.
That is the only real number you have as an x-intercept. Okay. So what that tells me is that my graph does something like that. My cubic, if this cubic was lifted, transferred up some units, wouldn't I have 2 more x-intercepts? That make sense, everybody? But let's just quickly graph what that would look like. If we go to, let me use GeoGebra because we can actually, I think GeoGebra has the ability to use I. Might have to be a capital I, I'm not sure. Well, let's not even do that. Let's do the work ourselves. What do you know about x plus 2i and x minus 2i? What'd you say, Sabrina? Close. They're the exact same terms, but the plus and the minus sign are different, right? Starts with a C. You do it in English. Conjugates, right? Okay. Would you conjugate?
You just said you did it in Spanish, and I would have got it.
Okay. Well, you do it in English too. You do it in any language. So you conjugate verbs and stuff, right? So these are conjugates. Okay. Well, conjugates in mathematics means that O and I are additive inverses. They cancel each other out. So this would be x minus 3 times x squared, right? Good. Plus 4. X squared plus 4. Is that right? 2. So this gives me negative 4i squared, right? What's I squared the same as? Negative 1. So I got negative 4 times negative 1, which is just positive 4, right? So let's see. I don't know if GeoGebra will do this. Let's go P of x, x minus 3, x minus 2i. I don't think it's going to know what I is. X plus 2i. I don't know if I go I, capital I. Nope. There's probably, I don't know if we can do it this way. Let's go P of X equals X minus 3, X plus 2 times square root of negative 1. That's 2I, right? And then let's go X minus 2 times square root of negative 1. See what that does. All right, so doesn't know what it's doing. Let's do this. Let's go P of X equals X minus 3, X squared plus 4. So that's us. That's the work we did, right?
Yeah.
Okay. Now we could actually expand that further. So could we FOIL this out? Get a P of X. That'd be like X to the third plus 4X minus 3X squared minus 12. And give you the same graph, same curve, but does that kind of mimic what we were drawing?
Okay.
Now I had more of a maximum, minimum type two turning points here. I think here we're seeing it probably have an inflection point, but it's a cubic. We only have one y-intercept. Okay, one x-intercept, and the reason for that is because the other two factors we come up with were actually non-real factors. Does that make sense? So it still breaks down to linear factors, but they don't have to be real. They don't have to be real numbers. They don't have to cross. When we break it down to factors, they don't necessarily have to always be actual x-intercepts or actual roots. Okay, and that's kind of the difference, in my opinion, of the terminology that we use for zeros. I don't think I'd call these zeros. Does that make sense? Okay, because they don't provide me a y value of 0 right here. Just food for thought. We might encounter that down the road. All right, so why are we doing this? What is the whole purpose? Okay. In the first example we did yesterday and then what we did today, they asked us to factor, and they gave us information right here, this question. They gave us this 1 right there. They told us, to get the ball rolling, we have to give you additional information because you don't know enough yet. Okay? Right now, I want to talk about how they knew to potentially ask you to try to use 1. They knew for some reason that 1 was a possibility. So I want to talk about why that is provided. I believe it's like the fans or whatever on some of those condensers on the roof of the.
I thought it was a dog.
Well, so you'd be able to hear that?
Yeah.
So you're a
I'm a dog.
All right. So 3.4 is getting us to basically take away that one extra piece of information that the author had to give us in order for us to factor. We should be able now, after this discussion, we should be able to factor anything on our own, okay? Without vaguely anything that has rational or integer coefficients, okay? And we'll talk about some other tools that can help if that does not happen for us. But we get what we call rational zeros of polynomials, okay? We'll talk about Descartes' rule of sign. So Descartes is the guy that came up with the XY plane, right? He was working on, he's very interested in polynomials, okay, and structures of them and seeing patterns with them, and he is credited with a lot of the stuff that we're talking about right now. So you may like him, you may dislike him. I would argue that we should like him because if it's not for him, then each one of these polynomials that we come across would be something we have to learn individually by itself and memorize or whatever by itself instead of learning these, what still may seem like difficult concepts, but they collectively allow us to learn about an infinite number of polynomials, which should be a little bit easier than learning an infinite number of singular polynomials. Okay? So he had this rule of signs that we're going to come up with a list of potential zeros that we have to check here. He came up with this rule of signs, this pattern that we can recognize to kind of make our original list. Our original list, guys, there are times where, just depending on what our values and our coefficients are, we might have a list of like 36 potential zeros. And then I have to go through and check systematically all 36 of those. That stinks. Okay? If we're paying attention to his rule of signs, based on our quotients, we might be able to figure out, okay, don't try any of these numbers in this list because of how this number produced a certain quotient. Okay? Same thing happens with the upper and lower bounds theorem. Our remainder and quotient line will allow us to say, okay, let's not check anything because of this value I use. I know nothing above that, or maybe nothing below that, will actually be a zero. There will be no x-intercepts in regards to those values. So these two things, I know it's kind of a vague description, and maybe you have absolutely no idea what I'm talking about. Those will come into play a little bit more on Monday. So here's the idea. And this is where, I don't know, last year you were told, we're going to take these P values, which are the factors of your constant term. You're going to take these Q values, which are the factors of your leading term coefficient, and you're going to divide them, and that gives you all your possible zeros. And we'll talk about that in a moment here anyways. But why? Okay? Here's the reason why. And it's kind of working in reverse. Okay? If I have a polynomial in factored form up there, in linear terms, x minus 2, x minus 3, x plus 4. If I were to FOIL that out, okay, I would probably take the first two, x minus 2 and x minus 3, FOIL those, get a quadratic, right? But my last times last would give me a positive 6, right? So now I have a quadratic times x plus 4. And I would distribute that out, but my last times last there would be a 6 times 4. 6 times 4 gives me that 24, right? Does that make sense, everybody? So here's the thing. Here's what this description is saying. If that's the process, if we multiply this out to get that, okay, that -2, that 3, and that 4, those values are zeros, right? Or we set those equal to 0 and solve for 2, 3, and -4. If those are zeros, then they had to be factors of that number right there. Does that make sense? Okay? So when we go through this process of saying, okay, take your constant term, we call it P, and you start finding the factors of it, the reason we're doing that is because of this logic right here. Okay? Because when I work from this direction to this direction, last times last times last actually gives me that number. Okay? Now it's a little bit more involved in that because this number right here is not always 1. Okay? It might be 2, it might be 3, it might be 4. And then this number here is not necessarily always, if this was a 3, then I have 3x minus 2, okay? Well, that 0 would actually be, what, 2/3? Okay? So then 2/3 becomes part of the number that multiplies the other, give me 24. So we have this idea here, which kind of generalizes it for whenever, regardless of what your leading term is, 1 or not 1, this process will work. It says if the polynomial P of x is your general polynomial, okay, has integer coefficients. This is where you said anything, you factor anything, well, anything that has integer coefficients. If it has rational coefficients like 2/3 or 4/5 or something like that, we can do something, okay, that will allow us to take that function and force that or integer coefficients. Just multiplication, but this will work right now just for integer coefficients. Okay, that's all we're going to focus on. We're not going to go kind of crazy right away with this stuff. We're going to go slow, and then we'll introduce those other types of polynomials that maybe don't follow this and how we can kind of morph them into this. Says your leading term has to be non-zero. Your leading coefficient has to be non-zero. That makes sense, I think. And your constant term has to be non-zero. You have to have a constant term. Okay. It says P and Q. P and Q. P is the factor of your constant term. Okay. P is a factor of your constant term. So your P over here are the factors of that term right there. Q are the factors of that term. Okay? Now this description here in the blue just says factor of A sub 0. Factor of A sub n. Okay? Because every rational zero is of that form. So when we set out to find all of our zeros, there's going to be multiple P over Q's, okay, that we're looking for. Okay? So that's why I use the phrase factors of P, factors of Q, instead of they're using singular here. Okay. Well, what does this mean to us? How do we do this? Okay? We'll start with a very, very simplistic one. These questions, guys, you can find out that they... No.
This just seems like a harder way to do it.
Well, what's the easier way? Using my calculator?
No, the...
Synthetic division?
Yeah,
Well, so here's the thing. We're going to use the synthetic division, but this tells us what to divide by. Okay? Because right now, synthetic division is what we're going to use. We're going to take this polynomial. We're trying to find the zeros of it. We're going to take that polynomial, coefficient of 1, coefficient of 0, coefficient of -3, coefficient of 2. And I'm going to say divide it. Use that synthetic division that you want to use. But what do you put in that box?
I feel like it's just...
You're just going to wing it? Okay? That's the thing. We don't want to wing it because our choices are the infinite numbers, right? Everything off the number line. Okay? What the rational root theorem says is if this is going to work, the factors of that number and the factors of that number are what you put in here as a quotient. So factors of P, we'll pick up with this on Monday. I'm going to open up an assignment, not due Monday, since you don't have anything to do tomorrow. Chuck, work on some math.
Yeah, dude, I just thought Kentucky was the funniest thing ever.